Hey, welcome back. In this lecture, let's implement the systick handler to do the context switch. I have written some comments here. First, we are going to do this part and I'm going to do this part later. In the first part, save the context of current task. First step here is, let's say you are running task 1 handler. Let's say you are running this code. So you are here and exception happened when you are printing this line, let's say. When the exception happens, the control will immediately come to the systick handler. You have to save the context of current task handler. First step is get current running task PSP value. And using that PSP value, store SF2 because SF1 is already stored. After that, save the current value of PSP in some global variable because we need that later. Let's do the first step. I'm going to use inline assembly code again, ASM. It should be a naked function. Let me do that later. Volatile. So get the current value of PSP. We have to use MRS instruction. Let's get that value to R0 PSP. And now using this PSP value, you have to store SF2, that is R4 to R11. Let's do that. This is like a push operation, but we can't use push instruction, remember, because this is a handler. If you use push instruction, what happens? MSP will be affected because in the handler mode, processor is always using MSP. Remember that. Here we have to store the register values into task private stack, isn't it? Which is referenced by the value of R0. This is a case of storing register value to memory. You should use a store instruction. Let's use store instruction, and the exact instruction which I want to use is stmdb, because we have to store multiple registers. We can use stmdb. db stands for decrement before. First you have to decrement, then you have to store. That is actually the push operation. So we have to simulate push operation. Decrement first, then store. That's why I'm selecting stmdb. Let's explore this instruction. stmdb, decrement the address before each access. You can get some examples here. You can see that this is a pointer or address and this is a register set. In our case, register set is R4 to R11. That's it. You have to give that register set in this bracket. Let's use this example code itself. Let me copy this. ASM, volatile. Here, let's modify this. This is a register list. We know that R4 to R11. And this is R0. What does this symbol do? That is to update R0 is an optional write back suffix. If this symbol is present, the final address that is loaded or stored to is written back to Rn. We want that, right? We want R0 to get updated after each store. That's why we have to use this exclamation symbol. After that, you have to save the current value of PSP. That means R0 value you have to store because that has the updated stack address of task private stack. To save that, I would call a function asm volatile. Do we have any save function? No. Let's create a save function. uint32_t save PSP value. Void. Oh, sorry. Here it is not void. Let's collect the value here. Tag addr. What we can do is this should be void. There is no return value. So just a parameter here, a receiving parameter. And here, let's store this value. PSP of task current task is equal to stack ADDR, or I can write current stack ADDR, or I can write simply current PSP value. That would be good. That's it. All you need to do is, in this code, you have to branch with link to this function, because R0 already has updated PSP value. That's why when you call this function, this argument will get the value of R0. That's according to the procedure called standard. We successfully saved R4 to R11, and SF1 is already stored during the exception sequence itself. And we saved the value of PSP. That's it. Current task state is saved successfully. Now the next step is retrieve the context of next task. For that, you have to decide what is the next task. So here, let's update the next task. For that, I'm going to call one function. Let me call it as update next task. Let's implement this function somewhere here. Void update next task. Basically, what this function does is it just does current task plus plus. That's it. And we know that we only have 4 tasks. So that's why current task is equal to, you should make this current task modulus 4 or max task. It should be within 0 to 3. Or I can write something like this. That's how we update the next task. That is round robin fashion. 0 becomes 1, 1 becomes 2, 2 becomes 3, and 3 becomes again 0. Next step is get its past PSP value. Now the current task is updated, so get its past PSP value. For that again, let's call ASM. We have already a function, right? This one, get PSP value. Let's use this code. Get PSP value. When get PSP value is called, what happens? Since current task is already updated, PSP of that current task will be returned. And the value is in the register R0. The return value is in R0. Next step is using that PSP value, retrieve SF2, that is R4 to R11. Now you have to use that PSP value which you got here and load from stack to register. Here you have to use load instruction. This is a data movement from memory to register. So that's why you have to use load instruction, and the instruction which I'm going to use is LDMIA. Let's explore that instruction. LDMIA. Load multiple registers and increment after. You have to increment the pointer. Here you can see that IA is increment address after each access. This is the default. You need not to use LDMIA. You can just use LDM. That's why I can copy this syntax LDM or LDMIA. Let me use LDMIA, and the pointer is R0. You have to give exclamation symbol here because I want to update this pointer whenever there is a load from memory to the register. The register list is R4 to R11. Here we have modified value of R0. That R0 you have to save to PSP. So that's why you have to update PSP, and for this you have to use MSR instruction because you have to store value from R0 to special register. Let's use MSR instruction. So let me copy this code, and the instruction is MSR PSP R0. After this line, you can exit the systick handler now. When you exit the systick handler, what happens? The exception exit sequences will take place automatically by the processor, and it tries to fetch the SF1, that is stack frame 1, where you have stored the return address and other things. Reference for that stack frame 1 is nothing but stack address of the next updated task. That's why you have modified the PSP here. The PSP got modified here. Now the PSP is pointing to the stack area of next updated task. That's why execution will go to the next task. And that's it. Compile this code and let's see whether we have any errors or not. Everything seems to be fine. Let me once again review this code to see whether there is any problem. You can actually give the prototype of all these functions later. Let's go to the main and let's see whether our sequences of calling functions are correct or not. First, false are enabled. That's correct. This is okay. This may be okay. I don't think any problem here. After that, init task stack, and after that we should configure the systick timer. That's okay. Then change the current stack pointer to PSP, then call task handler. After that, for every milliseconds, systick handler will execute and it should update the next task and it should schedule that. In the next lecture, let's test this and let's see whether we are able to see execution of multiple tasks. We are using printf, so we should see the output in ITM data console. And I'll see you in the next lecture.